I will complete quickly sometime today after class. Yeah. So the result, you did quite well. Yeah, much better than previous 2 years. Yeah. Yeah. So I do not worry. Yeah. So after I look at the results, I feel most of you can do very well in this class. Yeah. Even the later parts are a little harder than the first part. First part relatively easier. So the later we have, after we have 3 more assignments, homework assignments, usually a little harder than the first one. Yeah, but I feel most of you will be fine. Yeah. Yeah. All right, so that's the homework assignment part. Second, because some students ask me the question related to the quiz, so I feel, so probably in my first class when I talk about the syllabus, some of the students got some wrong impression, so here I want to explain. Yeah. Regarding the format of our assignments. Yeah. So let me explain. Based on those questions, let me try to clarify the formats of our assignments and together tests. So we have 2 tests, midterm and final. Okay, 2 tests. The format of these 2 tests, part A, part B. So let me start from the formats of the tests first, then assignments, to clarify the questions 2 students asked me. Yeah. Part A, 10 concept questions. Part B, 10 computation questions. Part A, 40 points. So 4 points each. Part B, 60 points. So 6 points each. And the part A, you do online. Yeah, even online. Yeah, part B. Yeah, part B. In person, but midterm I also give you online. Okay, yeah. So part B, midterm, online. Final, in person. Yeah, so that's the format. All right. Then, connecting to our homework assignments. So part A, map it to our quizzes, 6 quizzes. Yeah, we have, right, 6 quizzes. Oh, sorry. Oh. Six quizzes. Yeah. All right. Yeah. All right. So then, based on this one, yeah. So now I explain the question from 2 students. Yeah. So for each quiz, so now each quiz here. Yeah, I need to put a cloth. Each quiz, yeah, only 10 concept questions. Because, yeah, here you can see the logic. So the quiz corresponds to the part A. Okay, so that's the 10 concept questions. Online, yeah. Quiz all online. Okay. Yeah. Because those two students asked me a question like this. They understood in this way. Each quiz, part A, part B, online part, in-person part, or written part, not in person, computation question. It's not, okay? Quiz only online concept questions. Quiz, all the quizzes corresponds to, to the part A. Yeah. Then, homework assignments, so four homework assignments. Okay, corresponds to part B. Okay, yeah. 10 computation questions. Right. So 10 each. 10 computation questions. Now you see the logic. Okay? Yeah. So after I explain here, so then I hope those students, quite some students, they won't get confusion. Yeah. So still waiting for me to post, written part for quizzes. Yeah. No. Yeah. Because for your quiz 1, you didn't have the written part, right? Quiz 1, why quiz 2? Suddenly we changed the format. Yeah. Right. Yeah. So all the quizzes, so we use the same format. Yeah. All right. So that's the explanation. All right, so now let's start a lecture. Yeah. 8.3, homogeneous higher order linear ODEs. Here we do the generalization because we have seen the results of second order. Yeah. Very similar to the second order results. Yeah. Yeah. So here I just quickly go through the generalization part. All right. First, let's look at the format of the equations. So we use the standard format. Yeah. And here the assumptions. So I do not need to repeat the condition part. Yeah. Condition part, yeah. All these A coefficient functions. Yeah. Coefficient functions. Here we assume continuous. Yeah. We assume continuous. The reason we assume continuous from the existence and the uniqueness theorem, yeah, we learned last time. Because if they are continuous, then it is guaranteed this ODE, the existence of the solution is there. Yeah. So we can talk about solutions. Yeah. All right. Now let's look at the solution. Yeah. When we look at the solution here, yeah, we need to narrow down. Yeah, because even if these coefficient functions are continuous functions, they could be very complicated. Continuous function can be, very complicated. Yeah. So most of the time we cannot find the solutions in this case. So here we consider the simplest case. Yeah. we can always find solutions. So what is the simplest case? All these constant functions, little a functions, constant functions, they are constant. Yeah. They're constant. Yeah. Just like for second order ODE, we consider constant coefficients. Yeah. So here we generalize the result for the second order linear ODE. For the constant little a coefficients, then the solution function has this structure, e to the lambda x. Yeah. E to the lambda x. Yeah. The generalization from second order. Yeah. Then you just plug in. Yeah. So then, yeah, because each term has, after you take, in all those higher ordered derivatives, each term has this common factor, e to the lambda x. After cancellation, yeah, because this function can never be 0, right? The exponential function can never be 0. So we can cancel out this common factor. Then we get an algebraic equation. Yeah. So here we need to look at the solutions, the roots of this algebraic equation. Yeah. And here, because in our ODEs, in typical ODEs in engineering problems, all these constant coefficients, most of the time, yeah, real numbers. Yeah. It's rare we see the application problem complex numbers. Yeah. So here we assume all these coefficients are real numbers. But if they are complex numbers, still we can solve it. Yeah. Yeah. But here we just assume real numbers. Yeah. All right. Then there is a famous theorem about the roots of this equation. Yeah. So it is that theorem called the fundamental theorem of algebra. Yeah. Yeah. Very old, famous theorem about the solutions, the roots of this nth order algebraic equation. So it tells us every non-zero single variable, lambda single variable. Yeah. If multivariables, yeah, completely different. So this term can only be applied to single variable equation. Yeah. Degree n polynomial with complex. Yeah. The original, this fundamental theorem can be applied to the complex coefficients. Yeah. 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 But most of our interest is on the real coefficients. Yeah. So it works even for complex coefficients. Has counted with multiplicity. You know the multiplicity, right? The definition. Yeah. I mentioned once before this concept. So each root, because some of the roots may repeat it multiple times. Yeah. So when you have that situation, you need to count the same root multiple times, not just once. Yeah. Yeah. So for example, yeah, if you have some factor lambda minus lambda, let's say I, to the m I multiple times. Yeah, so there are other factors, right? Okay, other roots. Yeah, but for lambda I root, this root, particular root, you have the multiplicity mi. Yeah, so that's the. So you need to count this lambda I, not just once, mi times. Yeah, yeah, counting multiplicity, adding together. Okay, so you have, several roots several distinct roots. So then you count, adding their corresponding multiplicity numbers, exactly n complex roots. That's the result. And so degree n equation, then the number of complex roots. Yeah, because if you use complex coefficients, then so you need to expect to have complex roots. Yeah. The general case. Yeah. All right. Yeah. So this is the famous fundamental theorem of algebra, proved by famous mathematician Gauss. Yeah. Yeah. All right. Here we need to apply this theorem to find all the roots. Yeah. So actually study the roots. Yeah. To find the roots, now we have software, right? Yeah. So we, still that Wolfram alpha. Yeah. So we just use Wolfram alpha, we can find all the roots quickly. Yeah. All right. But here we need to study all the cases for the roots. Yeah. So let's have a discussion for those cases. Case 1. Yeah. Distinct real roots. Yeah. So the first case, we assume this polynomial has n distinct real roots. Yeah. Lambda 1, lambda 2, through lambda n. N roots, real roots. Then linearly, then we can get n linearly independent solutions. Yeah. In this one. Yeah. If we use the what's that? Wronskian. If we calculate the Wronskian on these n functions, we can show it's non-zero. Yeah. So we have the, although the calculation may not be that easy, but the calculation, yes. So because calculation you need to take derivatives, right? So each row derivatives, so all the way down. Yeah, but the higher degree, higher order of derivatives, you have the coefficient. Yeah, so here. Yeah. Because, so here, the derivatives. So if we take, let's say, case order derivatives on, let's say, e to the lambda 1 x. Yeah. Then you apply chain rules k times, so you have lambda 1 k times e to the lambda 1 x, right? Yeah. So then your k from 0, 1 through n minus 1, right? Yeah. But you can see there is a common factor. For each column, this e function is the common factor for each function. Yeah. So when you calculate the determinant, Wronskian determinant, you can take the common factor out. Right? So after you take common factor out, common factor out. Okay. Yeah. So that's the e part. Yeah. E part. Lambda 1 plus lambda 2 plus lambda n x, common factor out. Then inside you have determinant 1, lambda 2, lambda 1 squared. Yeah, I do not have enough space here. So 1, lambda 1 squared, and so on. Okay? So lambda 1 to the n minus 1. So that's the first, second, third, n. errors. This determinant, yeah, because if you calculate this determinant, you may feel too complicated, right? Yeah. Fortunately, the structure of this determinant, is very special. Yeah. So the matrix with this structure, matrix of this structure is called a Van der Waals matrix. Van der Waals matrix. So the Van der Waals determinant, there is a formula. There is a formula. Okay? Yeah. So the Van der Waals determinant. The difference, yeah. So you multiply the difference of all the roots. Okay? You calculate the difference. Then you multiply them. Because, so these roots, if the roots n distinct, yeah. So here, distinct, right? Yeah. Our first case, we assume distinct. That's important. Yeah. Otherwise, if not distinct, if you calculate, that could be 0. So we assume distinct. Then the difference of any two roots cannot be 0. Yeah. So then the determinant, Van der Waals determinant, the multiplication of all the differences of all possible differences of the two roots, non-zero. So the Wronskian non-zero, you know, they are linearly independent. Yeah. So for the first case, yeah. So you don't worry about these equations if they could be linearly dependent. Yeah. So you know it can be proved they must be linearly independent. That's case 1. Case 2, multiple real roots. This time we need to consider the multiplicity. Yeah. All right. If lambda, yeah. So we only need to describe the solutions, the form of the solutions for one real root repeated m times. Yeah. Then the remaining part, just do the similar things. Yeah. All right. If lambda is a real root of order m, then we can write m solutions. Yeah, m. So this number, m different solutions. Yeah. Yeah. Each one include the e function e to the lambda x. Then, yeah, to address the multiplicity, then the second different root, you multiply x to that e function. Third one, multiply x squared, and so on. Yeah. 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 In this way, we address that multiplicity problem. Yeah. Yeah. All right. Yeah. So there, this is just for one real root with multiplicity m. Yeah. So if you have several, each one you write solution functions in that form. Yeah. All right. That's case number 2. Yeah. Case number 3, simple complex roots. Simple. So what's the meaning of simple here? So each root is only, the multiplicity is 1. Yeah. Simple, we mean multiplicity equals 1. We call it simple root. Yeah. Yeah. All right? Yeah. So the multiplicity, simple means equals 1. Yeah. Simple complex roots. All right. Yeah, but here, yeah, in this case, we need to use our assumption all these a coefficients are real numbers. Yeah. This place we need to use. Yeah. 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 I mean, yeah. Actually, the first 2 cases we also assume. Yeah. So actually, yeah, here, let me put that. Otherwise, yeah. So in our application, So in our application, okay, yeah. So I mean, real world applications, yeah. So we assume that A0, A1, all the coefficients are real. All right? Yeah. Assumption. Then we can discuss case number 3. Okay? All right. So then, each complex root appears, complex. There. So if you have one complex root, then you have a conjugate pair. Okay? Yeah. So that is, so what's the conjugate pair? So if you have a complex root, if we write as gamma plus I omega, gamma omega 2 real coefficients. Yeah. So I omega, yeah. Then there must be a conjugate root, gamma minus I omega, in pair. Yeah, they appear in pairs, conjugate pairs. Yeah. Why is that? Because when we use the real coefficients and real coefficients, we can show that. Yeah, we can prove. Yeah, always. Yeah. Yeah. So in this case, then when we write our solutions, we need to use the conjugate pair structure. Sine, cosine, right? When you have conjugate pair, you can write sine and cosine. Yeah. So the solutions corresponding to the simple complex roots, you can use two. You can write two solutions. Yeah. Yeah. The real part, gamma is the real part. Yeah. So real part, you use E function. The complex part, omega is the complex part. Complex, not complex. We call the imaginary part, right? Yeah, complex, we mean the whole thing. Yeah, yeah. So imaginary part, yeah, omega. So we use cosine and sine. Yeah, that structure. Yeah. Because it's a simple complex root, so this y1, y2 only appear once. Yeah, only once. Yeah. Next, case number 4, we need to consider multiple complex roots. Yeah. So this conjugate pair, we may have multiplicity m greater than 1. Yeah. So this case, multiplicity greater than 1. And here I only use the double roots. Yeah, otherwise, we write too long. So I just write double roots. Okay. So the first 2 roots, yeah, same as the previous one. But the second one, yeah, you need to multiply extra x to the first. Yeah. Use this logic. If you have multiplicity 3, yeah, so the next 2, you need to multiply x squared to, the first 2 solutions. Yeah. So here, this is a double case. So you can easily generalize to, any multiplicity m case. Yeah. So that's for the higher order, nth order ODE, linear ODE, homogeneous linear with constant coefficients, with real constant coefficients. Yeah. If complex, then we don't have, the structure could be, very messy. Yeah. So we cannot write in this, these 4 cases, complex roots. Yeah. Each root, yeah, actually so first we don't have this conjugate case. Yeah. Yeah. So we have to use the complex way to write the solutions. We can still write n solutions, but in the complex ways. Yeah. All right. Yeah. So that's the then let's solve the higher order Euler-Cauchy equations. Yeah. Similar to the, the previous slide, yeah, but we just need to write our nth order ODE slightly different. Yeah. The structure like that, still constant coefficients. Yeah. All right. There we know we need to, each solution should take this power function form, x to the m, but here m could be arbitrary, so here the m. Yeah. What should be the m here? Yeah. So let me ask you that question. Yeah. Yeah. The number, yeah. So this m here in the exponent could be any complex number. Complex number. Could be a complex. Yeah. Yeah. Yeah, because our algebraic equation could have complex roots. So here you need to expect, yeah, m could be a complex number. Yeah. All right. So there, all the derivatives, yeah. So yeah. Then plugging, cancellation, x to the m, yeah, the common factor can be canceled out. Okay, yeah. All right. Yeah. So there you have a you have the nth order algebraic equation with m as the variable, right? M is the single variable. Single variable, then you can apply fundamental theorem of algebra, and m could be complex roots, right? Yeah. Yeah. Still, for cases, yeah, similar to what we have before. Yeah. So, yeah, basically I just copy from the previous slide, right? So I can go quickly. Yeah. In order k, yeah, we use k. But when you write, the form is slightly different. Okay. So for the multiple real roots, yeah, you need to, each one you need to multiply extra log, natural log of x function. Yeah. Yeah. In the previous slide we multiply x, right? Here we need to multiply natural log of x. Yeah. Yeah. Then multiplicity we have this power function. Then simple complex root, yeah, similar, but we need to use the natural log function. Yeah? So, yeah, natural log function. Yeah. For the, right. Yeah. All right, yeah. So then, multiplicity, so you add, so when you have the, right, so after the first two functions, the second two, you need to multiply extra natural log function. Okay? Yeah. And so on. Yeah. 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 So for the, you can see for the generalization, for the higher order, yeah. So you do this kind of generalization. Yeah. Yeah. Pretty straightforward. Yeah. All right. Yeah. But you need to, in your mind, the foundation for these two types of high order, that's the fundamental theorem of algebra. So you need to know that theorem a little bit. Yeah. All right. Yeah, so we finished this topic. All right. So the next topic, conversion of an nth order ODE to a system of ODEs, linear system. Yeah, yeah. So this view, this understanding, this view, also very useful. Yeah, yeah. And then later, yeah, because later we will solve linear system ODEs. Yeah. So we will apply linear algebra techniques to solve linear system of ODEs. Yeah. So after we do the conversion, yeah, so we just solve linear system of ODEs. Yeah. All right, so the conversion is very straightforward. Yeah. All right. General ODE form of nth order. Yeah. The general form could be very complicated. Yeah. The capital F function. Yeah. Could be very complex. Yeah. So most of the time we cannot solve this type of equations. Oh, yeah. Oh, so here let me say a few words. Yeah, because here we are talking about nth or higher order ODEs. In your second homework assignment, if you look at the questions a little bit, the second question I'll give you third order, but it's nonlinear ODE. Yeah. So the F function. So we can use this the general form. General form we do not require linear, right? So the nonlinear. So in that, our second problem, it's a nonlinear ODE. Yeah. If you look at it directly, pretty complicated. Yeah. Many terms, the product, derivatives, yeah. But there is a simple technique. Yeah. So you can simplify it a lot. So after you solve the first problem, I'll give you a hint, right? Yeah. So on the textbook, the page, So you need to solve the first problem, yeah, before you work on the second one. The first one, because you have experience, you apply the technique, reduction of order technique. So described on page 53. Yeah. Yeah. All right. After you complete that, then second problem, you apply the same technique. Okay. Reduction of order. Same technique as in the first question. So you can bring down, yeah, after you apply the technique, you will get a second order ODE, second order linear ODE with a very simple form. Yeah. So then you can solve that second order linear ODE with constant coefficients. Constant coefficients. Yeah. Very simple constant coefficients. After simplification, you have a simple second order ODE with constant coefficients. You can find solution easily, so you solve it. So then you're going back to the original solutions. Yeah. So that's the, yeah. So do not get scared. Yeah. Yeah, because the form of the equation is so complicated. Okay? So complicated. Yeah. So it's a nonlinear one. Yeah. But there is no x. Yeah. The reason that one, there is no x variable equation. O, y, y prime, y double prime, y triple prime, no x. So that is the sign for you to connect to that reduction of order technique. Yeah, reduction of order technique. Yeah, describe it on page 53. Yeah. Yeah. All right. Yeah. All right. Yeah. So that's the here. Yeah. If we can convert an nth order ODE to a linear, then we can apply many tools in linear algebra to solve the higher order ODE. Yeah. All right. All right. So here, all right. So let's make the connection. Yeah. Higher order ODE. So here, so you can see. Yeah. Now we need to do the conversion. All right. a solution function, yeah, y, one variable. Yeah. Yeah. So here the idea you can see. Yeah. Because we only need one solution function y. Yeah. All right. Yeah. One solution function y. Yeah. All right. Yeah. Yeah. So then, but in this capital F function, yeah, so other than this y, so if we look at from the symbol, yeah, symbol, other than y prime is another symbol, y double prime, another symbol, yeah. So although they are correlated, closely related, but they are different symbols, right? Yeah. Yeah. So here we use the views in this way. For different symbols, then we can use different functions. Yeah. So we treat different symbols as different functions. That view. Yeah. Yeah. All right. So a function of multiple variables. Yeah. So the first variable, second variable, yeah, multiple variables, treated as independent variables. Yeah. So independent variables. Then we plug in, right? Remember the last time I wrote this f function in the form of independent variables. Yeah. First we can write independent variables. Capital F of first variable x0, second variable x1, x2, and so on. Right? Yeah. So why? Yeah. 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 Because in this way, we will write n plus 1, right? Yeah. 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 Just the multiple variables. Okay. Yeah. Independent variables. Right? Yeah. The same f function, but later we can replace x0 by x, x1 by y, you know, x2 by y prime, and so on. Right? Yeah. So, all right. Yeah. So then, in that way, so we have this, you know, treated as independent variables. Yeah. All right. View on y part. Okay. Yeah. X part, we do not need to do anything, right? Because x is the original variable. X is the, you know, the variable we need to keep. Yeah. So we only do the conversion on y part. X part, we keep it. No conversion. Yeah. All right. So the high order derivatives on the same function. Yeah. All right. So we, yeah. Right. Yeah. So here our idea, yeah, higher order, we want to bring down the orders. Yeah. So the higher order, yeah, make it harder. Yeah. So we want to get a lower order derivatives. Lower order derivatives. All right. Yeah. But when you get a lower order derivatives, you need to pay. Because it's not free. That improvement is big. So you get something big, valuable, you need to pay for it. Okay? Yeah. So that means you need to do extra work to get it. Extra work. Extra effort to bring down the orders. Yeah. So let's look at what's the extra thing we need to do. All right. So the extra cost. Yeah. So we need to, yeah, because extra work result in extra cost. That part is more functions. We need to introduce more functions. Yeah, because here the solution function only one function. One y function is the solution function here. Yeah. The number of functions used in this equation very small, only 1. Yeah. Now, because we need to sacrifice to get some nice property, right? Yeah. Bring down the order of derivatives, that's nice property. To get that, we need to sacrifice in some other places. Yeah. That part, we need to use more functions. That's the sacrifice part. Because more functions means, you need to do some more work, right? Yeah. So when you find the solutions, you need to consider to find multiple solution functions in the system. Yeah. So that's what you need to pay more in this part. Okay, more function part. Yeah. Because you pay here. Yeah. So, and what do you get? Also, significant improvement. You reduce the orders of the derivatives. That's the idea. Okay. Yeah. All right. So let's look at how to make it happen. Yeah. All right. Conversion. All right. First order. Now, our goal, we only allow first order derivative in our equations. Okay? Yeah. First order. That's very, very good. First order. The lowest order of ODEs, right? Yeah. So we only use first order derivatives in our new equations. Yeah. All right. So the goal, convert the higher orders derivatives to first order derivatives with more functions. Yeah. Why you can do that? Yeah. So if some people may ask, why you can do that? You can make this conversion because we use more functions. If we use more functions, we can do it. Yeah. All right. So the trade-off between the orders of derivatives and the number of functions. Yeah. Yeah. All right. Yeah. So it is balanced. Yeah. The straightforward conversion. All right. Y, we convert to y1 function. Yeah. Y prime, we convert to, we denote it to y2 function, and so on. Yeah. Yeah. So here you can see, yeah, there, y double prime, y3 functions, and so on. Okay? Yeah. Yeah. The last one, yn function. Yeah. Yeah. So that's the first step. Yeah. And all these y1, y2, yn, these n unknown functions need to be solved from the given equation. Yeah. If you work on the original ODE, you only need to solve one y function, right? Yeah. But now, in this new system of ODE, you need to solve n different functions. y1, y2, through yn. Yeah. Yeah. In this aspect, it looks like you do more work, right? But the gain part is you never need to deal with higher order derivatives. You only need to deal with the first order derivatives. That's the gain part. Yeah. All right. So let's look at that. Yeah. So here you can see, because these n different functions, they are correlated in a special way. So this is the correlationship. So yk function equals yk minus 1 function prime. Yeah, you take derivative. Yeah. Prime, yeah, because one order higher, right? Yeah. So that's the simple relationship. Now you can write the whole system using this simple relationship. You can write this whole system. All right. Yeah. All right. Why? Yeah. So yeah. So here we work on this one. Yeah. Yeah. So this actually is not a general form. we assume, so here, we assume we have this function. Yeah. So here, we need to assume, yeah. Because here, we must make assumption, assume we have this form. Then we do the conversion. The conversion is like this, okay? Yeah. y1 prime equals y2. Okay? y2 prime equals y3. Yeah. So for the first n minus 1, very simple. Yeah. Very simple. The first n minus 1 equations, you can see addressing the relationship, yeah, among those n different functions. Yeah. Relationship. Yeah. So then the last one, yn prime equals this capital F function. Okay? Yeah. This multivariable capital F function. Now you can see in the whole, so we get a system. Yeah. We get a system. Yeah. All right. We get a system. In this whole system, you can see you only need to deal with first order derivatives, right? Yeah. So you won't see derivatives of order higher than 1. Yeah. 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 So only the first order derivatives. Yeah. So that's a nice thing. Yeah. Then the last question, yeah, before the break time, let me ask last question. Do we have a linear system? Yeah. So this is, after the conversion, we get this system. Yeah. Now I ask you, do you think at this point we have a linear system of ODEs? The answer is no. The answer is no. Why? Because we don't know the details of this capital F function, right? We don't know. The capital F function could be very complicated. So in general, this is not a linear system. Yeah. To get a linear system, we need to put an extra condition. When this capital F function linear, then we can get a linear system. Linear ODE system. Right? Yeah. So F, linear function. Yeah. So you know the meaning of linear function, right? Yeah. So yeah, because we define high order linear function ODEs several times before. Yeah. You just use the similar ways we used before. In the second order linear ODE, we have definition. Okay? Yeah. Yeah. So then similarly, high order, similar definition. Yeah. Here you use the similar way. Yeah. Yeah. So that is with respect, each variable, it must be linear. Yeah. Then no product of two different variables. Okay? Yeah. You cannot do any product of two variables. Yeah. You know, things like that. Yeah. All right. Yeah. So let's take a break. Yeah. Yeah. After